I'm RC Jim, and today we want to talk about ESC programming. These little guys right here, things that we use to control our motor and sort of determine how fast that thing is going to go. Of course, we could dive right into the programming cards and various things that you can use to program them. But really, before we do that, we need to really understand something about how they work. So, what is an ESC? Well, an ESC is an electronic speed control. Electronic speed control. It's going to be what controls how fast the motor is going to go and what sort of power is going to be delivered to it. Of course, the ESC has got 3 wires that come out of it, and those 3 wires hook up to 3 wires on your motor. And they're sending what we call a 3-phase current to the motor. It's different than your 3-phase electricity that you have with, say, if you've got 3-phase electricity in your shop running a heavy-duty motor or something like that. It's different than that in that those are sine wave going along as far as the power that's delivered. But with these, what you have is you've got power going to 2 of these leads, then power to the next 2, then power from the last one to the first one, power to the next one there, power to the second and third. The power is continuing to alternate between these different leads, and that basically is something that's going round and round in the motor as far as powering up coils, and those coils might be powered in a positive direction to create say a positive pole for the magnetic field, or the current could go through it the opposite direction, making it a negative pole. And each of those are pushing and pulling on the magnets that are going around on the outside of your outrunner, or if you got an in-runner, other way around. But it's all happening to make that thing go. So as you think about that, the typical diagram that we use to describe it is showing what's happening with a current in the motor. So you apply the electricity. So let's say we're down here we're talking about voltage, and up here we're talking about amps. Okay, so we got the voltage, say at 0 down here, and 0 amps there. And down here we apply voltage to the system at the level the battery goes to, and it goes for a certain period of time. Okay, so that's what the voltage does that's applied to the system. Okay, up here then, when the voltage is applied, the thing ramps up to a certain level of amps, and it takes some time for it to get up there, so it's going up on an angle. It holds it up there until the voltage is cut off, and then it's got a certain decay rate that comes down. So it doesn't just come down instantly. You're talking about amps, and you've got the current has been flowing through a coil, which has created magnetic flux. That magnetic flux doesn't just instantly stop, it keeps going, and as it keeps going, it's actually generating current in the same way that the thing was going before. See, it ramps up, gets to that maximum because it's had enough time to get up there, gets cut off, and it gradually decays down to nothing. Well, you got that for your first pulse of the 3. Well, before that one is cut off, most likely, you've got a next pulse that's coming. Okay? And as this power is put to the next 2 wires, so keep in mind this first pulse here, let's say it's going between these first 2 wires that I've got here. Okay? So the second pulse is going to go from that second wire to this one. So it's going to be involving some of the coils that were involved in this one to that one, but actually that's going to be going in the opposite direction now. If the current was going, say, this way before, that's down through this one. Now when these 2 are connected up, it's going to be going up and down through that one. So it's actually reversing what's happening inside there. Well, not inside here. Inside there with the motor as it switches to the next one. So you got through the first 2, then it switches to the next 2, so the voltage is applied. As the voltage is applied, it ramps up, and whether that is before or after that, I don't really know, but it ramps up to a certain point, holds it up there until the power gets cut off, and then again it decays back down again. Well, that's got us through 2 of the 3 phases, but then we get to the third one. And so the third one, the power kicks in, we've got voltage applied to the system down here. As the voltage is applied, it begins to ramp up, gets up to a maximum, but holds it there until the voltage is cut off. And as the voltage is cut off, it then decays, comes back down. And of course this thing is repeated, so there'll be another blue one happening in here, and another green one happening after that, and another red one happening after that. So it's all going along round and round and round, and round your motor goes. So that is what the ESC is doing. Now, as it's doing that, you might wonder, how does it know what to do and when to do it? Well, in actual fact, it depends on what's happening in the motor to know what to do with regard to this. So, think about your motor. Let's say, typically a lot of planes will have a outrunner, which means on your case you've got a bunch of magnets on the outside part of the case, and that's actually what's turning around. Because with any brushless DC motor, the magnets are the fixed magnets, or the permanent magnets, are the things that are going to spin. Because the other part of the motor is going to be some sort of set of coils, and of course there can be different numbers of magnets and different numbers of coils. The coils have got the wire wrapped around them, and with these coils, the wires can be directly wired to that without going through the commutator, because this part is fixed, it doesn't rotate. So the wires just go directly into there. This part is the part that's spinning, and those are just permanent magnets, so we can get by without brushes, hence a brushless DC motor. But what's actually happening is the ESC doesn't decide just, okay, we're going to run at 5,000 RPM, so we'll send a bunch of pulses that equal 5,000 RPM. It doesn't do that. This thing wouldn't know what to do, What the ESC does is it actually determines the position of the motor, and it says, oh, this particular coil here is between that one, and therefore, if, say, this one is plus and that one is minus, then what I need to do is and let's say we're going, it's a motor, and let's say we're looking at it from the front, so we want to go in that particular direction, then I want this thing to be minus here, so that it's going to be attracted to this one that it's approaching, and it's going to be pushed away from that one that it's just gone past. And it says, because the motor is in that position, that's what I want to happen to this one. And with this one here, minus, plus, minus, this one here, it's not quite to the minus one yet, so I want this one to be plus, so it'll repel that one and we'll get attracted to this one. And so it might be working with those two things right now to do that. It could be doing other things, whatever's going on there. But the ESC is actually detecting where the motor is, so it knows which pulse to send and where to send it. And you might wonder, how on earth does it do that? Well, there are some motors that have a sensor in them, but typically with our aircraft, we don't need that, and we want to save weight, so why add extra power or parts and weight and stuff like that. So what we do is that because this thing is spinning all the time anyway, every time one of these coils goes past a magnet, whether or not the thing is powered up or not, that magnet has an influence on what's going on in that coil, and that magnet will pull some electronic flux through that coil, which will create a little tiny bit of a current going in a particular direction. And as the ESC sees what's happening to each of the coils in there, it can detect the precise position of that motor to where it can send the right pulse to the right place. So the motor is actually determining the rate of how often these pulses are happening. Well, that's all well and good, but you might then wonder, well, how on earth then do you control how fast the motor is going? If the motor is determining it, but I want to control the motor, not it to control me, what's going on here? Well, what you actually do is you vary the amount of power going to the motor. Now, you might do that for each of these voltage pulses just to be a percent of the total voltage, But electronically, in terms of the components required for that, it would be pretty complicated and you'd have a very heavy system, and we don't particularly like that. So you can actually get the equivalent by dividing these things up to where the average voltage is less. So instead of sending one solid pulse all the way through this whole period of time that it's supposed to be happening, what we do is we break that up into individual pulses separated by a time where it's not on. And so we got this low sort of power setting. We might have these two little pulses of voltage that are applied. By having a period of time where it's off and a period of time where it's on, you'd have an average voltage that is equivalent to, that will then determine how much power the motor has, and how much power the motor has is going to determine how fast it goes. If you don't have much power, it can't spin the prop very fast. If you give it a lot of power, it can spin it very fast. And so that's the way that we actually control that. Now the next question is how do you know when to send these little pulses? Well, that's what we call the PWM frequency, the pulse width modulation frequency. And that's how often these little pulses are going to be happening along here of electricity. So we've got a pulse width modulation frequency that determines how often these things are going to happen. And then the question is, how do they fit in with these standard set of pulses that we want to generate? Does it get triggered every time a pulse is supposed to start, or how does that work? Well, in actual fact, you got a little oscillator or something here in the ESC that is operating at a certain frequency, and every time it hits the start of that frequency, it's going to kick it on, and then it's going to hold it on for as long as you've got the throttle set for. The throttle is sending a signal to the ESC, and that's telling it how long to keep this on, what sort of duty cycle to have. And by the way, the duty cycle is, like I said, the expression of this throttle level, but it has to do with the percentage of time that the power is applied. So if we are at say a 30% throttle setting, then 30% of the time the power is applied, 70% of the time the power is off. And so you get an average of 30% of the power over time. So full throttle is going to be 100% duty cycle, zero throttle is going to be 0%. 4/10 way up the stick should give you a 40% duty cycle, and so forth. So that's duty cycle. So the pulse width modulation frequency is telling you how often these pulses are going to happen. And when they happen, it's just going to have a look at what needs what, and it's going to send that to it. So if the blue needs power, it's going to be sending to it. This first one, the red would be in there as well, so it would also be sending the red signal for that period of time. It's going to then cut off based on the throttle setting. When the pulse width modulation frequency says, yes, it's time to send another pulse, it has a look and sees what is needed where. It'll send that, and on it goes. Now, typically when you see this explained, people draw these bars up on that chart right there. Doesn't work. This is current, that's voltage. You know, voltage you can turn on and off. You know, it's either there or it's not there. But what's actually happening to the electrons is quite different. Just like up here, you know, this ramping up is not because the ESC says, oh, let's go little by little, you know, let's not give it everything all at once, let's take some time to get it up there. No, it's not that at all. It's because of the impedance within the motor. Voltage gets applied. As the voltage gets applied, current starts to flow through the windings. There's resistance in the windings, so it doesn't instantly get up there. There's also impedance based on the magnetic flux that's being generated by the coil that's there. That sort of slows it down. And so it takes a period of time to get up there, even if it is a millifraction of a millisecond, you know, sort of a thing. But nonetheless, it takes time to get up there. Well, when we got these individual pulses happening, the same thing is taking place. You can't have just a straight bar up here and say that's what's happening to the current. In actual fact, you turn the current on right here, it starts to go up, and where you turn the current off, up here someplace, that is going to be where it stops, you know, and it's going to start to decay. Let's see, where we got here, yeah, so we're saying that right there is the point where it stops. So it's going to start to decay until it gets turned on again. In this case, it's not getting turned on again until over here, and so it's actually going to come all the way down and go up to there until it turns on again. And it'll be keep doing something like that until it gets up to here, and then it's going to say, oops, time to turn off, and it'll turn off. So you'll actually be seeing things like this happen with regard to the current. So just keep in mind that people like to get confused as to what they're looking at. Voltage and current are two different things. But seeing what's happening there, it's pretty easy to see why that with your plane at partial throttle, things are pretty easy on the motor and on the ESC because the current is really low. Current is what's going to be generating heat as it goes through resistance. That reduction in power from the current times the resistance is going to be equivalent to what sort of heat is being generated. So as currents stay very, very low, very little heat, but boy, as it ramps up there and it stays up there, lots and lots of heat, and you can see the difference in area here compared to the difference in area up there, and that is a huge difference along the way. Okay, now we mentioned that a pulse width modulation frequency is what determines when these voltages get turned on and off. So then the question might be, given that that's programmable and you can choose different frequencies, which one do you want? Well, as you think about having multiple pulses, down here when it's real small, it doesn't make an awful lot of difference, but you can imagine as these things get bigger, let's say we hit the throttle and we go up to, let's say about a 60% throttle level, something like that. So 60% it's going to be on, so we come over here and we now have all of this that is the power, not the power, the voltage that's being provided to the system. Okay, and then it kicks in again over here and it goes up to, you know, maybe just shy of where it would normally turn off, you know, so, you know, something like that. Okay, up here it's then going to go farther. Let's get rid of those. So it's going to go all the way up until it gets up to there, and then it's going to start coming back down again. But now, just a little while later, it's going to get triggered again. So it comes down to that point, and now it wants to go up again. And it starts to go up until it gets just short of there, and then it comes down. Now, there you got two pulses in the one thing. You can imagine if this was happening a lot more rapid, instead of this big jag that you have here, you would have a situation where you would have little tiny things up there, and it would be much closer to the shape of this. And as you think about what's happening in the motor, with each of these big jags, you got sort of a push and then not a push and a push and not of a push, and that's the type of thing that can create vibration, and vibration creates noise, and you know. So with the fewer pulses, it will tend to not run as smooth as what it does with very, very rapid pulses and lots of them in there. So the motor would kind of like you to have a super high pulse width modulation frequency as far as the motor running sweetly. But the problem is that as you think about this decay that's happening here, okay, what's happening inside the motor, you've got the electricity that's going through these coils, it's generating magnetic flux, and that magnetic flux can't just stop instantly. It keeps flowing, and as it's flowing, it's generating electricity in there, and somehow they got to bring that down to nothing. So what the motor, or actually the ESC is doing inside it, it's got some circuitry in there where it's dumping the current that's spinning around in here. It's dumping the current to bring it down to nothing. There's two different ways to do that. One is what they call freewheeling, and freewheeling has nothing to do with how easy the motor spins. It has to do with electricity spinning around inside here. With a freewheeling, it uses another FET transistor to dump the electricity, and that has very little resistance, and so it doesn't generate a lot of heat when it's coming down. But the other style, the cheaper one and the one that's more common, is non-freewheeling, and with that one it has resistance, a higher resistance, and so every time when you cut off the power, it's going to be creating heat. So if you cut off the power 2 times per pulse, that's 2 times whatever the heat is of one thing. But if you cut it off 10 times per pulse, then that's 10 times the heat. And so having the very fine pulse width modulation, a very high, fast, high frequency pulse modulation is going to make the ESC run a lot hotter. So then the question is, where is the trade-off? How do you sort of work that out? Well, from the test results that I've seen, there's about a 2% difference in power going to the high frequency as compared to the lowest acceptable frequency on an ESC. So you take the lowest frequency that allows the motor to run smoothly as compared to the highest frequency that's available, there's about a 2% difference in power. Well, as you go from 4.2 volts down to 3.7 or whatever you're going for, that's much more of a difference than 2%. So 2% isn't much, as far as I don't think you'd feel it, but the ESC is definitely going to feel that heat, So most of us, we will err on the side of caution. We will protect our ESC, and what we're going to do is choose a pulse width modulation frequency that is as low as what will allow the motor to run smoothly with that setting in the ESC. Okay, just a couple more observations with regard to what we have here. I've mentioned this before, but when you think about the voltage that's being delivered by the ESC isn't changing that. Okay, it's not a voltage regulator, apart from what happens in your battery elimination circuit where it's delivering 6 volts, that's regulated. But as far as the power that's going to the motor, it's just being switched on and off. That's all that's happening. So if, well, first off, with different batteries, if you have a 5-cell battery, the voltage is going to be the 5-cell voltage that's going through there. If you got a 3-cell battery, it's going to be the 3-cell with the same ESC. It's not changing the voltage. At the start of your flight, the voltage is going to be 4.2 volts per cell or so. At the end of it, it might be 3.8, 3.7, what it might be that you're targeting. So that's going to change, and that changes the maximum RPM that you can get out of your motor, and it has impact on some other things as well. So that's an important thing to consider. Now, another thing to think about is that given that this pulse width modulation is triggering a certain rate of these pulses that are coming out, and this pulse width modulation frequency is something that's set on your ESC, so until you reset it, it's going to stay the same, and that frequency is going to stay the same no matter what throttle setting you're at. If you're running the motor real slow, you are going to get a lot of pulses, or a lot of little jabs of electricity per one of these sort of pulse-shaped things that we're working with. It can be a whole bunch of them. And if you're at full throttle, generally we are targeting a setting on the pulse width modulation frequency that's just a little bit higher than the frequency of these pulses that are taking place. And so at full throttle, it's just on all the time. But as you get up close to full throttle, where it's just coming just shy of that thing, you may just get 1 per pulse per one of these pulses based on the pulse width modulation frequency, and it might cut off the end of this one and the front of that one, and then the end of that one and front of the next one, and that kind of thing. You won't be getting lots and lots of things happening up at that up near full throttle. It'll be pretty well just simply 1 pulse per thing, and generally that works fine. So that's what we're generally going to target at a as a setting for the pulse width modulation frequency, as we'll try to work out how often these pulses are going to be taking place, and then make sure that the pulse width modulation frequency is just a little bit higher than what's needed. Now if it gets lower than what's needed, then you got a big problem, and then you might miss a complete pulse or whatever, and you can have a very rough running motor and very noisy, and we'll talk about that a little bit later. Okay, with regard to programming the ESC, the one thing that you always have to do with a new airplane or one that you've just acquired is to make sure that your throttle is calibrated. You want to make sure that full throttle really is full throttle, and obviously that no throttle is no throttle. So the way you do that, first off, you get everything set up, so get all your control surfaces working properly, going in the right direction and all that kind of thing. You can do your modes and, you know, low rates, high rates, mid rates, you know, various things like that. Get all that stuff working and everything, and that is fine. And so then you've got your plane bound to the transmitter. You got both of them on. You have your stick down at the bottom and so forth. So then you turn off the power to the airplane, and you make sure that the airplane is safe. So you either have the prop taken off, or you've got the thing fixed in place to where it can't go anywhere, and the prop is not some place where it can damage yourself or something else. Okay, so the plane is turned off, the transmitter is still turned on, and it has just been bound to the plane. You then put the power all the way to maximum on the transmitter, and with the thing all the way in maximum, heaven forbid, you turn on the power on the airplane. Okay? You'll then hear a few beeps from the ESC, and having heard those few beeps, you immediately take the stick down to nothing. You'll then get some other beeps that confirm that the job is done, and with that, it's programmed. The throttle really is at 100% at 100%, and 0 at 0. Okay, so that's one thing you always do, and you do that with a stick on the transmitter. But there are a lot of other things that you can program on your airplane, and you might just wonder, well, what are they? Well, besides the throttle calibration, you've got the brake. Now, as you think about what's happening in the motor, we talked about how that when you cut off the power, the magnetic flux going through the coil is generating some current. Well, when you've got a brake set, it actually uses that current to send power to the coils in the opposite direction that it would normally be going. And that actually functions as a brake. So the thing is generating its own electricity as the thing is slowing down. It's sending that electricity through the coils in such a way that instead of powering the motor forward, it's trying to power it backwards, and trying to power it backwards will stop it in a hurry. And of course, once it's stopped, the current has stopped flowing and it's stopped. Okay? So that's what the brake is doing. Now, as far as when to use a brake, that will get used on, say, like sailplanes with a folding prop. In order for the prop to fold into the fuselage, it needs to stop spinning, and you might need to have the brake to be able to get it to stop spinning, so it'll fold it in. You might want to use a brake on a plane that doesn't have landing gear and that you hand launch, and you're going to belly land it in. It's less likely that the prop is going to get broken if it isn't spinning. For one thing, you got a good possibility that when it hits the prop, it's going to be horizontal instead of vertical. But even when it's vertical, it'll tend to just sort of pop out of the way, and it doesn't have all that extra momentum that happens as the prop is naturally spinning. Apart from that, a spinning prop is going to create more drag than a stationary prop, and if you are thinking about, say, a dead stick landing, the plane is going to go farther if you got the brake on than what it would with the brake off. But for me, that's not really a big issue, and in particular, I kind of like the idea of the free spinning prop slowing the plane down, in that we've got a flying field of trees at each end, and it's kind of nice to have something to slow the plane down, especially if you don't have flaps, to be able to get it down and get it stopped well before the end of the flying field. So that's probably not a big deal. But something that is very significant, and that is what we told you about the ESC being able to determine the position of the motor based on where the little pulses of electricity are coming back. That only happens when the motor is turning. If that motor is stopped, the ESC has no idea of what position the motor is in. And so what it'll have to do is it'll send a pulse of electricity to jerk it a little bit, and then of course all of this is happening in very short periods of time, but anyway, it moves it a little bit, and then it sees what gets triggered, and it says, oh, that's where I need to send the electricity. And so then it can start initiating, the power on sort of thing, sending the pulses of electricity to the right places at the right time. So having the brake off with the prop spinning in the air is going to make the plane more responsive if you're doing things to where you're shooting up in the air and you cut the throttle off and you do a hammerhead or something and you want to hit the throttle again, or you're doing something where you're doing on-off type things with the motor. It's going to perform better if you don't have the brake on. And I suppose as well, there's just sort of that thought of, it just looks odd with a plane coming in without the prop spinning. It seems nice to have it going around. Now another thing that you can program with your ESC is the direction of rotation. Clockwise versus counterclockwise, or reverse that. Now naturally, as you hook up the motor to the ESC, you can swap any two of these leads back opposite, and that will reverse the direction of the motor. But you can also do it with the ESC, and just in the programming, set it to either normal or reverse. Having mentioned that, I'm reminded and humbled by a situation where I got sort of a bit of a brain fade one day, and I had got a plane and was owned by somebody else before, but they'd never flown it. And so anyway, I got the plane, got it all set up, went through all kinds of stuff with it, all kinds of testing and things like that. And so then one day I decided I'm going to take it to the field. Well, I remembered that a few days before I'd gone through everything, had the thing running and all that kind of stuff, so I figured everything is normal and everything is fine. So I take it to the field, I get to the bench and check all of the control surfaces, I do my range check and all of those things, everything is sweet, but I didn't run the motor. And so anyway, I carry the plane up to the flight line and set it down and get up there in the flight box ready to go off with it, and gave the throttle a blip and the thing went backwards. And I go, oh, I thought I had this thing all set up. What's going on here, And so anyway, this is where the second brain fade. First brain fade is I, should have checked that on the bench, if not at home, and all of that. But then the second thing, and usually these things come in multiples to create a disaster, but the second thing was that immediately in my head I think, oh, I can reverse things on my transmitter. I know how to do that. I know all about this thing. I get in there and I get into my servo mode and I pick channel reverse and I go in here, servo setup. Instead of travel, I'm going to pick reverse, and I'll just reverse the throttle. Dummy. Reversing the throttle, all of that does is it means that instead of this being off and that being full throttle, it means that now is off and this is full throttle. So I got the stick down and I put that thing in there with the thing all hooked up, and boom, the plane takes off full throttle going backwards. And it took me a few moments to work out what was going on to push the stick up and get the thing to stop. But boy, right in front of all the club members that were there, and I'm supposedly the guy that is supposed to know these things, and that was an extremely humbling experience. Okay, So I share that with you so that you can avoid being humbled in a similar way and realize that you don't reverse the throttle with your transmitter to get the engine to spin in the opposite direction. You either switch two of the wires, just swap them opposite the way they were before for any two of the wires, or get into your programming and use that to reverse it. And always, always, always double, triple check everything before you get started. Okay, now PWM frequency. We mentioned you can program that in your radio. Now typically there's going to be a whole bunch of individual choices that you can select from. So it won't be a dial-in set of range, but it'll say, you know, 8 kilohertz or 16 kilohertz or 32 kilohertz or, you know, whatever it might be. So you'll have those particular choices that you can select from. So how can we work out what pulse width modulation frequency we need? Pulse width modulation frequency. Okay, well, there's a formula that's typically used for this, and essentially what the the formula does, it says, okay, take your kV rating, the RPM per volts, times the number of volts, times the number of poles, and divide that by 20. And that will give you the answer in hertz, that is cycles per second. And typically in your ESC program, it's going to give you choices in kilohertz, so you'll be dividing that by 1,000. So if that comes out to 20,000, that's 20 kilohertz. And if you came up with 20 kilohertz in the formula, you just pick the next higher option. So let's say it's got 18 and 24 as two of the selections. You wouldn't pick 18 if it's 20, you'd pick the 24. You check to make sure it operates okay. If the thing starts screaming when it gets up to high RPMs, and screaming, what I mean is very noisy scream, then you say, oop, I need a little bit higher yet. So you bump it up a little bit higher until it finally is running properly. Now, in my head, I've got a few questions about this. For one thing, many times when you see this formula, they specify nominal voltage there. So for a LiPo, 3.7 volts per cell. But we've already noted that as the voltage goes up, the RPMs that the motor's going to develop goes up due to this kV. So wouldn't you want to use the maximum voltage that would be possible? So 4.2 volts per cell. To me, that's what I'd be using there rather than nominal voltage. The other thing is the question of whether this thing really applies when we got a huge outrunner with zillions of, you know, well, not zillions, but, you know, 10, 20, 30, you know, whatever magnets around the outside and dozen or so, you know, coils on the inside. Does it still apply? And so for that, I think about why they've come up with this formula and how the thing fits. So you think of kV. kV is revolutions per minute, RPM, per volt. Multiply it times volts, and we can then cross out the volts, just thinking about our what we got, our units, how the units are going to come out, and that's basically how we're going to work this out. And then you got times poles per revolution. So for each revolution, you're going to go through so many of these magnets around the outside, so poles per revolution. Okay, and then we've got a three-phase thing happening with the coils in there. So just forgetting about how many of them there are, we're saying that it's only going in three-phase, so we're saying for each magnet, three things can happen to it. So we got three, we'll call it cycles, per pole. Okay, so now we got pole on the top, pole on the bottom. We can cross those ones out. Then of course we've got revolution on the bottom here and revolution on the top there, so you can cross those out. So then the only thing is we're working in hertz, and we've got cycles per second there, and here we've got cycles per minute, so we need to convert minutes into seconds, and so we realize that, well, 60 seconds is 1 minute, and so then we can cross out the minutes, and we end up getting cycles per second. And you got a 60 on the bottom, a 3 on the top, and divide the 3 into 60, it goes in 20 times, and so that's why you got a 20 on the bottom. So essentially what that tells me is that they're assuming that for every revolution, any one magnet only goes through 3 electric cycles. So for your 3 phases, those 3 phases only happen to one magnet one time. Maybe that's true. So that's something I'll be working on to try and understand myself. And when I understand it, I'll share it for those of you that care. Most of you don't, but some of us enjoy working out such things. But what I will tell you is that first off, generally whatever the default value is for this in your ESC, most of the time that's going to be fine. Okay. If you use that, and as you crank up the RPM, if you start getting a lot of noise out of the motor, then go in there and put it to a higher level. And in particular, if you've got a outrunner with lots of magnets in it, it's going to need a higher kV rating. Okay, they're not kV, kilohertz as far as the PWM frequency is concerned. But essentially, just get it high enough to where the motor is running smoothly and you're not getting a racket up at the high RPM levels, and keeping in mind that it's at the high RPM levels where you might get things that get dropped out. Lower RPM, you know, even at low values of this, you're going to get multiple pulses of electricity for every one of these shape things that we're trying to replicate. So lower RPMs is not going to be an issue, but up at high RPMs, that's where the thing could get noisy, and who knows what sort of damage that might be doing to your motor. You know, if it's running sweetly, the way it's all set up, that's good enough, and you don't need to worry about all of that. So that's the PWM frequency. Okay, slow start is another option that you can have. Now, slow start is important where you've got a big motor and you've got some sort of gear train that the thing is attached to it, such as with a helicopter, where it's got to spin up a whole bunch of gears and things like that. Great big motor attached to a whole bunch of gears. If you get it an instant start, this thing will really give a whammy amount of torque as it gets going, and it's liable to bust something. Okay, so if you've got something where there's a great big load, you might want a slow start, and that would mainly be applications where it's hooked up to gears, some cars, helicopters, things like that. And perhaps maybe in some airplanes where it's swinging some huge prop, you might want a slow start with that. Some ESCs will give you a more than 2 selections. You know, it's more than just slow and fast. They might give you a medium one. And so say in that situation where you got a plane with a huge prop on it and you want to take it easy, you might use one of those middle settings rather than the absolute slow one. I can say I've flown a plane with it on the slow start, and you can do that, but it acts weird. I like so much better having the slow start turned off. Now, related to slow start and the helicopters, you also have on many ESCs a Heli or a governor mode. And what the governor mode does is with your throttle stick, instead of determining how much power is going to the motor, it will actually determine the level of RPM it wants the motor to run at. And so if you take it up there to halfway with no load on the thing, you know, you've got no collective dialed in, it's sitting on the ground, the blades are just simply spinning around level and very little load on it. It knows that that's the RPM that's associated with that. You dial in the collective, and as the collective comes in, the load goes up, but the ESC will seek to maintain that same RPM with the stick in that position. If you move the stick to another position, it'll target a different RPM. So you move the stick up, it'll be targeting a higher RPM. Now the danger with this is when you're using it with airplanes and it's got the Heli mode in there. I think I've had this experience, at least I've been warned that it might have been what happened. But I had a rather large plane, a 6S battery in it, good big motor in it, and all of that type of thing. And I got a bit lazy, and I landed the plane. I was just going to go around to take off again, and I didn't think about holding the elevator stick back as I was taxiing on the grass. And I'd given it the throttle, and it nosed over, and the prop dug into the ground. Well, it was only a second or two. I mean, it was just so brief. I mean, just immediately when it happened, I pulled back on the throttle. But, you know, I go over there to look at the plane and smoke is coming up out of it. And I'd cooked the ESC. Well, that was a YEP ESC. And what a fellow club member told me is that oftentimes the YEP ESCs will come in that Heli mode. And when you're just operating it in normal conditions, you don't know the difference. You know, you push it up, it goes faster. You pull it down, it goes slower. But you get into a situation where it's digging into the ground, or heaven forbid, into your hand. It is going to up the power to keep that RPM going no matter what is going on, and that can be rather dangerous. Okay, so if you've got a Heli mode, make sure that the Heli mode is turned off. And it's sometimes referred to as a governor mode. You can also select the battery type, and that's usually between a nickel-based battery and a lithium-based battery. So nickel metal hydride versus a LiPo. The main difference there is the ESC is going to be trying to protect you from the voltage going too low. And what a too low voltage is going to be different for a nickel-based battery as compared to a lithium-based battery. So it's just letting it know about that. Timing is another issue that you can look at. Now with timing, it has to do with when this pulse of electricity comes in relation to the position of the coil. Now it's a little bit like timing in a car. You know, you remember back in the good old days when we had distributors and, you know, all that kind of thing, and you could turn the distributor cap to change the time. Oh yeah, that's before you were born, you know, but some of us are old enough to remember such things. But that had to do with when the spark would be fired as compared to when the piston was up there. And even though you want the burning mixture inside the cylinder to be pushing down on the cylinder, you actually fire the spark plug before the piston gets all the way up to the top. And there's an optimum place there because it takes time for that flame front to move through that combustion chamber. It takes a certain amount of time to build up that amount of pressure that you want to be pushed down on that thing. And it's sort of played around as to what sort of thing that is. And of course nowadays with the computer operated engines and stuff like that, is varying that timing for all kinds of different situations, the amount of load on the motor and the RPM and, you know, you name it. Back in our days, it was in the olden days, you know, good old days, we just had a centrifugal weight in the distributor that as it spun faster, it changed the timing. But anyway, similar on a brushless DC motor in that there's sort of an optimum time to energize the coil based on the position of the magnet, given that it takes time for that current to get up there. The magnetic flux that's being generated inside that coil is related to the amount of current going through the coil. And if the thing is going so fast that it can't even get up there until the magnet has already passed it, that's going to be a problem. So in some cases, even though the start of this thing might be happening at a time that it's going to be detrimental, because it's going to be so beneficial to have the full current flowing, the full magnetic flux at a certain amount of time, it would be beneficial to advance the timing and to trigger the voltage early so that the maximum magnetic flux is developed exactly when you need it. So they have different timing settings that can be there. Again, for a large brushless DC motor, that has lots of magnets, it's going to tend to have a higher timing rate that is needed. And for simple motors and in-runners and various things like that, often it'll be a lower rate. Usually the default setting is going to be okay, but you can play around with it. And fortunately, a lot of ESCs have got an automatic function. I don't know about you, but while manual gear shifts are a lot of fun and they can be pretty cool, in terms of practicality, pretty hard to beat an automatic. So with your timing, the automatic is certainly a good choice. Well, that pretty well does it with regard to what an ESC does and various things in it that can be changed and why you might want to change them and things such as that. On our next video, we're going to go through more detail on the how-tos, either with your transmitter using the throttle stick or using a programming card. And that will be a generic thing that sort of, generally applies to most ESCs and programming cards. But then we're going to follow that with a series of videos on specific ESCs and programming cards where we actually use their card and their ESC and see what it does and perhaps even do some testing with that. So there's a lot more things yet to come. So what you need to do right now is make sure that you subscribe to our channel so that you're in touch with all of this, and then have a look at some of our other videos, and I think you'll find them helpful. Have a great day.